Ladies and gentlemen, the second to last video lesson in the discrete unit. In this one, we'll talk about the sum of arithmetic and geometric sequences, which is called a series. Summation notation is a notation that's used to express a sum, or a series, without writing too much. George Riemann is the mathematician who came up with this notation, so it's also called a Riemann sum. Here it is. The sum of the terms of the sequence, whatever the sequence is, 1, 2, 3, 4, 5, 2, 4, 6, 8, 10, or some other one, it's denoted by this notation. We have the capital sigma right in the middle there, and then we have a lower limit and an upper limit. The lower limit, k equals 1, is called the index of summation. That's the point at which you start. So when you look at the back of the book, you see an index and you're looking for a topic. It'll tell you the page number, and that's where that topic starts. The upper limit is n, and it could be any number, but we're using discrete numbers. So we're going from 1 to n, and we have an example we'll do in a moment. And then that Riemann sum is basically taking the sum of all of the terms in the sequence a sub k. So it's read the sum of a sub k from k equals 1 to n. Note that the n doesn't tell you how many things to add up. It tells you the last number to plug in to the sequence. Let's do some examples together, and I recommend that you write these down. In example 1, we're being told to expand the sum, but in example 2, we're asked to write the sum in summation notation. All right, so with the first one, we have the Riemann sum from k equals 2 to 6. That means we'll have 2, 3, 4, 5, 6, 5 terms. The one that we plug in 2 for, 3, 4, 5, and 6. And what we do with those numbers is we simply plug them in into the expression that's listed there, 1 over k. So our first term is 1 over 2. Our second term, 1 over 3. 1 over 4, 1 over 5, 1 over 6. And what that summation notation is telling us to actually do is add up those terms. So whatever the sum of all of those terms are is the value of the Riemann sum. But the list of those numbers written out is called a sequence, and when we add those numbers together, it's called a series. Example 2, write the sum in summation notation. So what this sum is telling us is we're adding 1 and 8 and 27 and every number after that. So we could continue the sequence, find out what the next number is, and then add that number, which makes it a part of the series. Or we could just think about what these numbers are representing. So what I like to do is I like to write down what term number is each number, so each term. So this is term number 1, and term number 2, and term number 3. So now we have to think about how do we get from 1 to 1? What do we have to do to this 1 to get to 1? Well, we can multiply by 1, or we could raise 1 to a power. All right, that doesn't tell us much. Now we'll go to 2. What do we have to do to 2 to get to 8? Well, I can multiply by 4, but I could also raise it to a power. Because that has the same pattern involved as the 1, that's where I'm leaning towards. Now if I raise 3 to a power, can I get 27? And so what I could do with these now is the fact that 1 plus 8 plus 27 is equal to, well, it's 1 cubed plus 2 cubed plus 3 cubed. 3 cubed. And that goes on forever. So in order to write this in summation notation, what I could do is I could start at k equals 1, and I could go up to infinity. And this expression is basically k raised to that third power. And that is the summation notation for that series. So it's a little bit of guessing and checking and playing with the numbers. I have one last little bonus thought for writing summation notation, and that's this down here. To get even terms, what we have to do is we need to take whatever variable we're given, or whatever we're using in that case, which is usually up to us. We have to do this. We need to multiply that variable by 2. Now to get odd terms, what we need to do is multiply by 2 as well, and then add an odd number. So that odd number is usually like 1 or 3 or 5. Okay. So for example, if we're finding the sum and we're plugging in 1 and 2 and 3 and 4, we need to multiply by 2 to get that, to make that 1 and the 3, everything odd, even. But when we're doing odd terms, if we have terms that are odd, to get those terms, we need to make every odd and every even first even so that we could add something consistent, an odd number, to make it odd. Sigma notation is summation notation. It's a Riemann sum. We're using the Greek letter sigma, and we're adding up all of these terms. I'm going to have you do these 5 questions on your own. There's a place to put your work and the answers in your booklet. And so what we're doing is you're just writing out the terms for each Riemann sum and then finding out what the actual sum is by adding them together. Pause now, see what you could do, and come back. I'll have the answers. Okay, there we have it. I'm pretty sure I didn't make any mistakes. The answer to the last one is 1/3. I have some insight for you from Carl Frederic Gauss. This will help us understand one of the formulas I present to you in the next slide. So turn the page in your booklet and you'll see it there. One of the famous legends in the lore of mathematics concerns the German mathematician Carl Friedrich Gauss. His mathematical talent was apparent at a very early age. One version of the story has Gauss at age 10 being in a class that was challenged by the teacher to add up all the numbers from 1 to 100. While his classmates were still writing down the problem, Gauss walked to the front of the room to present his slate to the teacher. Yes, his slate. The teacher, certain that Gauss could only be guessing, he was gaussing, refused to look at his answer. Gauss simply placed it face down on the teacher's desk, declared, "There it is," and returned to his seat. Later, after all the slates had been collected, the teacher looked at Gauss's work, which consisted of a single number, the correct answer, and no other student got it right. So the important feature of the legend for mathematicians is how the young Gauss got the answer so quickly. And so we're going to do that together here, and it's pretty cool. And it helps us understand the formula so much easier. So on your paper, what I want you to do is play along with me here. And what we're doing is step number 1. On a wide piece of paper, so that's our paper, write the sum 1 to 100. So here we go. I have 1. Make some space over here for the 1, 2, and 3. You'll see why in a moment. We use ... 98, 99, 100. Now, step 2, what we're going to do is write the whole thing backwards. And you'll start to see what we're doing and why we're doing it. All right, so that's 3 plus 2 plus 1. I forgot the pluses up here. All right, then in the third column, or third row, in the third step, we're adding numbers 2 by 2. So 101, 101, 101. And this is basically what Carl Friedrich Gauss did when he was much younger than you. Sorry. Step 4 says, what's the sum of the 100 identical numbers in part 3? Well, the sum is 101. Let me write this. Sum equals 101. So we have 101 all the way across the row. And there are 100 of them, because if you look at that first row, we see we go from 1 to 100. Right? So that means we have 101 times 100, which is, well, 101, 0, 0, 10,100. Now, step 5 says, explain why half of the answer in part 4 is the actual answer to the challenge. Now, we don't need a calculator for this, so step 5 down here is saying, well, the actual sum is half of that because we added the second row just to help us calculate that. So half of 10,000 is 5,000. Half of 100 is 50. And that is the actual sum of the numbers 1 through 100. So we'll use that and create a formula from that. Turn back a page to go to the sum of a finite arithmetic sequence. So that's on the left. And all I really want you to do is write this part. While this is a semi-good formula, you can write it, sure. Really, this is what we did in the last step. We added the first term and the last term, divided by 2, and multiplied how many terms we had. So we had 100 terms, 1 plus 100, the first and the last term, and divide by 2. So let's apply that to a fairly basic sequence so we understand what's actually going on here. And so we have these 6 terms listed for us in example 2, and we're going to find the sum of the arithmetic sequence. So what we could do is just add up these 6 terms, right? Pretty simple. But if we have a little bit more terms than we really want, maybe like 50 or 80, then it's really helpful to have the formula. So what we'll do first is we'll write out using the formula. There it is. We have 6 terms, so n is 6. And we take the first term and the last term, add them up, divided by 2. If you're not sure what the last term is, then you just have to figure it out. So we have 6 times 6 over 2, and which is 6 times 3, which is 18. Now, what if we just added those up together, right? We just did it by hand, which if that was the case, we might as well just do that. So what we have is -7 and -3 is -10, and 1 plus 5 is 6, and 9 plus 3 is 22. And so then that equals -4 plus 22, which equals 18. And those two things are the same. But I encourage you to use the formula so you could get familiar with it. The last concept in this lesson is the sum of a finite geometric sequence. Another way to describe that is a finite geometric series, because a series is a sum of a sequence. Okay, so here's the definition on the left, so you should write that down. The main thing is just knowing this information here. And I'm just asking you to commit this formula to memory and apply it to a few questions. So what this is saying is you would take the first term, a sub 1, and multiply it by 1 minus r to the n. And we divide it by 1 minus r. You know, I could describe why that formula is, but seriously, it's just not worth it. Our focus in lesson 5b is to talk more about that, and it will make more sense. So let's take a look at the example. We have 1, 2, 3, 4 terms, and then we have what seems to be like a 10th term. Oh, and by the way, there's a little error. There should be a 4 right there. So this is 4 times -1/3 to the 10. So how do we do this? What we need to do is figure out how this relates to the explicit formula for a geometric sequence. And what I see is in this expression right here, or right here, what that's telling us is that the first term is 4. A sub 1 is 4. And then what the r value is, the common ratio, is -1/3. Getting kind of sloppy here. -1/3. And then because the general form, the explicit form of a geometric sequence is a r to the n minus 1, n minus 1 in this case is 10. So therefore n equals 11. That's one of the little tricks, little weird things that shows up in that. So all we got to do is think about what that last term that we're adding in the sequence and relate that to the formula over here, the explicit formula, and we can find out which term that is. So if that's a large number, you just kind of solve using any of the previous math that you know. So we'll just use the formula here, and this is not that exciting for me, so I'm assuming it's not that exciting for you. So that would be a sub 1, which is 4, times 1 minus -1/3 to the n, so the n is 11, and then we're going to divide by 1 minus r, 1 minus -1/3. And there is the sum of that finite geometric sequence. Now, one last point here is you'll see this number is really close to the number 3. So you should start to think like, well, what if I added up all of the terms of this geometric sequence, meaning an infinite geometric sequence? Would that mean that the sum would actually be exactly 3? And that's what we're going to talk about in the next lesson, which is way more interesting and ties into Calc BC topics, the last unit that we study in Calc BC. Okay, well, thanks for adding stuff up with me. I really appreciate it. Take care now. Bye-bye.